Okay, so here for the first part, find the zeros of the function. You got to basically find the roots. So where is your y value? Basically 0. So you get x is 1 basically at that point. Now second is, so there's only one root, that's 1 comma 0. Now second is equation of the vertical asymptotes. So equation of asymptotes is here, for vertical asymptote, equate denominator to 0. So if I equate x squared to 0, so get x as 0. And for horizontal asymptote, as you can see, the numerator or the coefficient of, I mean, this linear or quadratic. Okay, I can do this question in multiple ways. So horizontal asymptote, actually, when you show, it is like 18, uh, let's say x minus 1 over x squared. So as I can just break this down as 18 x over x squared minus 1 over x squared. This becomes 18 1 over x minus 1 over x squared. So now when so here it is x over x squared. Yeah. So now logically what happened is that if I pick up the value of as x tends to infinity, now what happened is that this becomes a 0. So this is 0. So 18 times 0 minus 0 basically. So that is 0. So the horizontal asymptote both the side, as x tends to positive infinity, that's your y is 0. And also when x tends to negative infinity, you can see y is 0. So it means that both the sides the horizontal asymptote is y is 0. It means x-axis is the horizontal asymptote. As far as the shortcut is concerned here, we look at whether it's linear or quadratic. If it is the degree of numerator is lower than degree of denominator, so in that case, what happens is that the horizontal asymptote automatically becomes y equals to 0. Now, next up is find out the coordinates of local maximum and justify its maximum. So firstly, for maximum or minimum, you do f dash x equate to 0. So already has been given f dash x, so 18 times 2 minus x over x cube equals to 0. So I get x is 2. Now, just to check what's the exact y value here, whether it's maximum or minimum, you plug in the double derivative. So if I plug this in double derivative, we get 36 times 2 minus 3 over 2 cubed, 2 to the power 4, which is coming as negative. Hence, it is a maximum. Now, the maximum value actually you get by plugging x as 2 in the original function. So if I plug in the original function, so 18 times 1 over 4, so which is 4.5. So this is basically the exact maximum value. Now to find out the function where it is concave up. So for concave up or down, you got to draw the sign diagram for double derivative. So here I take 0 as the vertical asymptote of the double derivative, as you can see, and 3 at the second critical point, because if you look at the numerator, changes the sign about 3. Now take a value which is higher than 3, it's positive. Take a value which is lower than 3, it will be negative. So and beyond the 0, if I take minus, so it's minus here, so overall it'll be negative. So it's concave up for x more than 3. You can clearly see that it's concave up means it's like a minimum, because where your double derivative is positive, we call it as concave up. And hence now we got to sketch the graph. How is the graph of this look like? So 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 the graph is entirely concave down. You can see the entirely concave down for this range. And so if I have to sketch the final graph for this function, so if I take, this is the x-axis here, so there is a vertical asymptote at 0. So I'm just going to draw a vertical asymptote here quickly. So this is the vertical asymptote here, and at 1 there was a root. At 2 there is a maximum value, which is 4.5. At 3 there is a point of inflection basically. There is some y value at 3 is 18 times 2 over 9. So it'll be some numerical value, which is going to be obviously lower than 4.5, because 4.5 is maximum. So here, since the graph is concave down, as you can see, it is going to be till here, 4.5 until this point. And then after 3, it becomes concave up. So concave up in this range. Now, and the next axis is the horizontal asymptote. And here in the left side, you can see the graph is actually concave down throughout, and x-axis is horizontal asymptote. So if I write down, if I draw the graph here, actually it'll be incorrect because the graph will become concave up. So you got to be careful and take the inferences from all the perspectives. So here we have the graph that is concave down, and so it is fine that a graph crosses the horizontal asymptote, because horizontal asymptote is actually significant at infinity. So that's something which needs to get verified.